about the resolution to this cliffhanger. Remember that we were looking at an open container of water. So it's got some liquid and it's got some vapor. All right, and we set this system at some temperature T. So we put this in a box, a bath, if you will. All right, bath at T. We apply a constant pressure, an external pressure, that's our atmosphere. Say, for instance, remember we defined the standard pressure, which is atmospheric pressure, 1 bar. Right? So we have a constant pressure, right? And our air, if you will, is allowed to exchange with the vapor of the water so that the pressure is always 1 bar. Right? So sometimes these little water molecules are leaving, and then some gas is coming in to exchange it, and so on and so forth. And the water is allowed to equilibrate, if you will, and move between the vapor and the liquid phase, right? So there's some motion, if you will, of molecules in and out of the liquor phase, the liquid phase from the atoms, right? So we have this exchange of this coexistence, right? Coexistence of vapor and liquid at some temperature. And occasionally I'll spell vapor like a Canadian with a U. Sometimes I won't. It's up to you how you want to spell it at temperature T and P. Temperature T and pressure P naught. Okay. Right, so we talked about, how do we measure the thermodynamics of this process, right? And we came up with enthalpy as the way that we measure this. Right, so we measure, so this reaction is tracked heat transfer or energy transfer between the liquid. That's not liquid. Let me write it out more specifically, sorry. Between liquid and gas phases tracked by delta H, the enthalpy of vaporization. And again, there's nothing special about the enthalpy of vaporization. It's just the heat change that occurs in the system when you go from liquid to water, right? This just refers to H2O liquid goes to H2O gas. And it releases or absorbs some amount of heat. Right, so the question, of course, therefore, is all we're asking is how much energy does the water release or absorb when it vaporizes, right? So we looked at this, right? We looked it up on Webbook and ATCT, looked up some values, calculated them at different temperatures, right? And we were interested in what happens at boiling, right? So if T is about 100 C, right, boiling, we saw that delta vap enthalpy of water was about 40 kilojoules per mole, give or take. We saw this value change depending on the temperature, right? The standard enthalpy of vaporization at 298, right? Standard conditions is about 44. And what that means is that at boiling, it takes another basically 4 less kilojoules mole of energy to vaporize the water. Okay, and that should make sense that it should go down. It requires less energy at higher temperature, right? Because you can just logically intuit yourself that, hey, when I boil water, it's easier to boil at high temperature than it is low temperature, so it requires less energy. But again, the thing that we didn't really quite understand when we did this calculation at the end of class was that this says that the system requires some input of heat at 100 C for it to boil. Right? It says it takes 40 kilojoules a mole to vaporize that water at boiling. Right? But if you take a pot open pot of boiling water that's equilibrated to 100 C and put it on the counter, you don't have to put any heat into it, it just boils, right? It boils spontaneously. Right? So it seems like, from this perspective, it requires energy to put in to get it to boil, but if you raise the heat high enough, it just boils on its own. Right? You don't have to put any input heat into it. You can just heat it up to 212, take it off the pot, and it continues to boil, assuming it doesn't dissipate the heat. Right? Eventually it cools off. There's reason to do that, but assuming it can't cool off, it will just continue to boil and boil. So what are we missing here, right? This says that we have a kind of a deficiency of energy, right? We need to put in an extra 40 in there to get it to boil, but it goes at 100 C, regardless of putting energy into the system or not. Right? It's spontaneous, it just occurs. So we're missing half the story here, if you will. Right? We know that it takes that much energy to boil, but clearly that energy is already available in the system at 100 C for it to boil. Otherwise, it wouldn't happen spontaneously. The energy must be available somewhere, right, for it to do it on its own. So we have to think about where that energy comes from. Okay? And again, all we're doing here is heat, right? We're just heating the system, and we're noticing that the system changes from being majority liquid, starts to vaporize, and eventually it boils. Right? So the only thing that's changing is heat. So that must mean that the energy that's available for this process to continue by itself at 100 C must come from heat as well, because it's the only thing it's transferring, it's just heat. There must be some sink of heat energy that's available in our experiment, if you will, that the system is pulling from, where basically this heat reservoir, if you will, has enough heat in it to drive the boiling at 100 C, has enough energy into it. So we have to figure out how we measure that discrepancy, if you will. Right? Why is it that when it's at 40 kilojoules per mole, water just boils spontaneously? Okay, so we have to add another number here. H is not the only thing we need. All right, so I want to introduce that concept to you today. And of course, not surprisingly, because it has to do with heat, it has to do with entropy. We've not really considered how entropy or heat is flowing from the flask to the outside. And what we're going to find is that when we consider how entropy flows, right, remember, entropy is all this heat that's being used for just basically nothing, just for spontaneous randomness, if you will. And that's temperature dependent. But the heat available to the system, the entropy available to the system, is what drives the system forward into a spontaneous process at boiling point. So let's look at this carefully. Bless you. Sorry, my screen is acting up. There we go. Why are you over there? Okay. So let's look at a very simple case first, okay? So let's simplify our box a little bit, and we'll come up with a nice little expression here. So instead of, what I'm going to do, I'm going to build a box, all right, that's sealed. All right, so it's a closed box. We have a closed box, right, and it's at some volume V. Okay, it's got volume V, and inside of that I'm going to put a water bath inside of this, and then immersed in the water bath I'm going to put my open flask. Okay, and then I'll just have some magic material that we're vaporizing in here. Okay, so this is a constant volume box. Right? And what we're going to do to measure anything about this box is we're going to stick a thermometer in the box. Sorry. So we have a thermometer right here. All right, so here's my thermometer. thermometer. And inside of this box, I'm going to add like a heating coil or something like that. You know, something to heat the water. Right? We have a heating coil in here. Right? And we have a little heating element. We'll just call this a heating element. All right, so what this does is it allows us to, this is heat coming off of it, right? Right, this allows us to, it's kind of like your calorimeter, actually, right? The calorimeter in PChem lab, this rotation. Right? You have a heating element inside of this water. The system is sealed and insulated. You have some chemical process occurring in your flask, and it's allowed to equilibrate with the box, but the box is at fixed volume. Okay? And so the pressure, therefore, will change. As you vaporize the gas, the pressure will build, right, inside the chamber, and the temperature will rise. Okay, so let's just very quickly think about the energy of this box, the change in energy of the box. So again, P changing, T changing. The energy of this box, remember, is going to be du TdS minus PdV. Right? That's our first law of thermodynamics, right? But we can simplify this, right? Because dV is 0. It's a constant volume box. So this goes to 0 by definition. All right, so any heat, what does this mean? It says, well, any change in the energy of the box is purely entropic. It's just heat. Right? It just basically says that all energy in this system is heat energy. No work, all heat. Okay. So now what I want to think about is what do I need to do to this box, to my sample? Let's say I have water in that flask. What do I need to do, what condition do I need to satisfy in order to get the water to boil? Okay. So boil spontaneously. Okay. Right? I don't mean physically, like we get to force it to boil, but basically I keep raising the temperature and suddenly it starts to boil. Okay. What do I need? What do I need to satisfy? Well, the reaction has some change in energy, right? So if there's no work, so in the box or in the flask, if PdV is small, then we can always say that the change in enthalpy is approximately change in U, right? We talked about how that is a valid assumption, right? And when we first talked about entropy, the total change in energy is basically the heat. That's certainly probably valid here for the most part, because the volume is not changing. And so for the vaporization, right, for the vaporization of the energy, or for the water at 212 Fahrenheit, we need to crank the temperature up to 100 C. And then we saw that the amount of energy required to vaporize the liquid at that temperature is 40 kilojoules per mole. DH was 40 kilojoules. Right, so for water, for H2O, that means that the change in energy must be at least greater than or equal to delta H vap of this reaction, right? And that's greater than roughly 40 kilojoules per mole at 373 Kelvin. Okay, so that means that we have to, with our heater, put in at least this much energy at 212 to get it to boil. Okay? Well, but du is also equal to TdS. All right, so this has something to do with the entropy change of that process, right? So what this is saying is that at constant volume, at CV, constant volume, that du is greater than TdS, which implies that the entropy change, that the amount of energy supplied, must be greater than the entropy change of the process. Okay, so what I can do is therefore say that if du is greater than, do I have this wrong? Sorry, I have this wrong. I apologize. Wrong side. Remember that entropy is always increasing, right? Remember, entropy always has to be increasing, so I have the sign flip. Right, so if the system is changing by 40 kilojoules per mole of energy, for this system to go to completion, the total entropy change times the temperature heat constant has to be greater than that. Right, this is the second law of thermodynamics, right? We require that, remember that for all processes, that S is maximum and ds is always greater than 0. Right? Always has to be increasing.
I have a question.
Yes, ma'am.
Then what about like for the du greater than the delta H for vaporization? Like why would that be greater? Like in the yellow.
Right, right. So I have it flipped. I apologize.
Okay.
Yeah, you're right. You're right. Sorry. Thank you. Yeah, you're exactly right. Greater than dH. Okay. All right, so the supplied energy has to be greater than the, or sorry, less than the entropy change. So this is also minus. All right, so the ds. So what that means is that ds minus du over t is greater than 0, which means that tds minus du has to be greater than 0. All right, so what this means is that the total change in entropy of the system has to be greater than the amount of energy required for the process. Right? Remember, the system always has to be disordered. And in the world, the universe is always going to require a certain amount of entropy from a process for it to go forward. And that's got to be a larger number than the energy required for the process. Right? The process is going to take some amount of energy, right, to get done, but Mother Nature's always like, well, I need a little bit of entropy on the side as well, right? It always needs its fix. And so that means that the total entropy change of the system has to be greater at that temperature than the required amount of energy for the process. Basically, the entropy has to ultimately drive the system. There has to be enough heat in the total system, which is the whole volume of the box. This box, there has to be enough heat energy to supply this change. Right, so this,
I have another question.
yeah, go ahead.
So how come I'm still like a little bit confused when you do like the ds minus du over t is greater than 0. Like I don't see why you would know that.
I'm sorry, say it again.
Like for the ds minus du over t
Yeah.
being greater than 0. Like why do you know that?
Subtract TDS from both sides of this equation that I just did, right? And then
Okay.
divide by T.
Okay. And then, but if you have TDS minus DU, isn't DU equal to TDS?
Yes. Yes, that's in the box. So what I'm looking at here is changes inside of the flask. So the flask, the internal pressure or the internal kind of density and the pressure inside the flask will change. The balance of the liquid and the gas will change. So that at a certain time, there may be more gas evolving from the water than there would be at a different temperature. And so this is from the perspective of the flask, not the box. The total box is equal. So the total entropy of the box is equal to the total change in entropy or energy of the whole box. But of this process, we have to consider the enthalpy required to complete this process as well as the entropy change of this process as well, and those may be different.
Okay.
Okay, so let me say this is the total heat energy of the box. And the way that we've written this is the energy required for the vaporization. Okay, so what that means is that you can put energy into, right, we can heat the system up, and what you're actually doing is, if you think about the gas inside, if you think about the water inside the flask versus the water in the outside of the flask, inside the box, the gas outside of the box, right, because it's allowed to exchange, gas allowed to fly out. Right, we're applying, right, in order to get it to vaporize, you have to put in 40 kilojoules a mole of energy in there, okay? And what this criteria says is that the total box has to have a total heat content greater than that requirement for it to be spontaneous. The idea is that the total entropy of the box at some temperature must supply enough energy to the water in the flask to vaporize it. And how much energy does the water require? Well, it requires DH, which is 40 kilojoules per mole. So the total heat energy of the box, which includes the molecules floating around this volume as well as the molecules inside the box, or inside the flask, their total entropy, heat energy, if you will, TDS, has to be greater than that 40 kilojoules per mole. Right? So the box has to supply at least the right amount of thermal energy to get this process going. And that's dependent on temperature. So what that's saying is that I need to, in order for this gas to vaporize, this liquid to vaporize spontaneously, I need 40 kilojoules per mole. And for it to be spontaneous, something has to give it automatically that energy, and that's going to be the molecules in the total box. And the amount of energy that those molecules have in total in the box is TDS. And the boiling doesn't occur until those molecules have enough heat energy to transfer to the liquid water to vaporize it. Right? So what everything does in the box is provide that water the energy it needs to vaporize, and that doesn't happen until the boiling point, where TDS is going to be basically the same as DPU. So it's not until 100 Celsius that our atmosphere, or our box, if you will, has enough thermal energy to drive the boiling. And that's where TDS is going to be 40 kilojoules per mole. Right? So the box is using heat to drive the change. You use thermal energy to drive this chemical, this physical change to the gas, and you need enough of that heat energy in the box in your system to drive that change. So the box has to supply enough energy. We'll see this again in just a second. So what we want to think about now is we want to think about the enthalpy of what we want to think about is the balance of the enthalpy of our process, which is the energy required to do it, and how much heat energy is provided by the whole system. And that's the flask as well as the exterior, the total entropy of the experiment. So in the case of our flask sitting in the lab, we want to think about the entropy change of the material inside of our flask, but we also want to think about the entropy being provided, the heat energy being provided by the warm bath as well. That's also a sink and source of energy for the enthalpy, the process that requires enthalpy. Right? So this is like if you think this is how much energy you have in the bank from Mother Nature, and this is how much you require. And so you should always have more in the bank. You should never overdraft, right? So if you have to overdraft energy to complete a process, it won't be spontaneous. Okay, so you always have to have enough energy in the bank. So what we want to think about now is to define a function, like enthalpy, that allows us to calculate this balance of entropy and enthalpy. Right? We have a enthalpic requirement from our process. I need this much energy removed or this much energy added. And then we have a source of energy, which is our bath at some temperature T, that provides entropy as a source of energy to drive that process spontaneously. So we want to think about the balance of entropy and enthalpy, if you will. And that balance is going to tell us whether a reaction is going to, or a process is going to happen spontaneously, or it's not going to happen at all. For some reason, it's putting my... So let's define that function. All right, so let me go back one page real quick. Let me take my picture. Oops. I want this picture here. Okay. So here we go. Here's our chemistry experiment. All right. Oops. Sorry, I have it disappeared into the page. There we go. And then we have a box here, sorry. Okay, so what I want to do now is I want to define a new function, a thermodynamic function that we can use like enthalpy for this system. All right, so now we're going to define a function g for our constant pressure system. G is a function. And G is defined to be the enthalpy of the system or the process minus Ts, T delta S. Okay, once again, this looks a lot like what we just discussed, right? This is the balance of the requirement that the process has of energy, whether it's negative or positive, depends. Sometimes processes release energy, sometimes they absorb them. And Ts is how much energy our flask in our bath and our system at T has available to use for the enthalpy, right? So we have to think again how energy flows, because H may suggest energy flows out, which might mean that entropy needs to flow in the opposite direction, or vice versa, right? It could flow in, heat may flow in different directions depending on the signs of these things, right? So we'll have to think about that a little bit. All right, and so this is this kind of balance here. Gibbs, and of course everyone knows what this is, right? This is Gibbs free energy. Right, so let's just kind of very simply think a little bit about what G tells us. Okay, so let's, again, G can be as a number. Again, this is in units of joules, joules per mole, kilojoules per mole, whatever energy. It's the energy, right? Free energy, right? It's in joules, right? So let's think about what the value might imply about the spontaneity of this process. So first, maybe I should define spontaneity. Right, spontaneity, a spontaneous process is, definition, maybe I've defined this before, but I'll just do it again. Spontaneous process. And by process, I mean it could be a phase change, it could be a reaction, it could be anything. A compression, expansion, anything you can think of is one that occurs with no external input of force or energy. Right? It's a process that just occurs. Okay? And Gibbs is going to tell us something about whether at a given temperature if something occurs spontaneously or not. Right? And Gibbs is our way to track spontaneity. So Gibbs energy determines the spontaneity of a process at temperature T and pressure P. And it's also a function of the number of moles as well. So Gibbs is just is truly a function of what we call an NPT ensemble. Right, this is what we call a chemical ensemble. Right? This is the kind of assumption that you make when you go into wet lab in organic chemistry, right? You have a fixed amount of molecules, you start 1 mole of product, reactants, you have a fixed pressure, that's your atmospheric pressure, and you fix the temperature, right? And Gibbs tells you something about the energy behavior, thermodynamics of those conditions. It's a chemical ensemble. All right, and so G can be basically three different classes of values. So if this is kind of like a case by case, a case. So if G is greater than 0, what does that mean? Well, that means that enthalpy is greater than Ts, right? Right? And we just said that means that the reaction or the process requires more energy than the entropy has available. So this is a non-spontaneous process. Not enough entropy change to drive process forward. Right? That should make sense. Right? Another, and now when we talk about equilibrium, this will come back. G greater than 0 also means it's a reactant-favored process. Think about a reaction being spontaneous means that the reactants go straight to products, right? So if G is greater than 0, that means the reaction's not spontaneous. It means it's mostly reactants, not products in equilibrium. Well, again, we're not there yet, but just Gen Chem concepts. And then we'll look at G less than 0, of course. That's where H is less than Ts. Right, this is spontaneous for the opposite reason why G greater than 0 is non-spontaneous. Right, we call that product favored. Right, a reaction has a negative delta G is a product favored. Right? Spontaneous to go to products. Now, what does G equals 0 imply? Well, that means that the enthalpy is exactly the right amount required by entropy. The entropy change of the process is balanced out by the enthalpic requirements, right? So what does this mean? Well, this actually means at equilibrium. Right? The term we call this is at equilibrium, which means that forward process equally likely as reverse. Okay. So this means that if you have a process that's G equals 0, it can go, it's just as likely to go forward as it is backwards. Okay, we call this the equilibrium. All right, we'll see how that ties into the concept of chemical equilibrium when we get to it. But G equals 0 is important for that consideration. Okay. You should make sure that you're trying to distinguish yourself a little bit here from delta G of reactions that we learned in organic and general chemistry. Okay, it's the same concept. Right? Gibbs here is the same concept as delta G of reaction in Gen Chem. All right, and we'll talk about but there are slight differences here, because this G can be defined at any N, P, and T. Right? So you can have a system out of chemical equilibrium. Say, for instance, you expect there to be a 1-to-1 mixture, let's say a 2-to-1 mixture of reactant to products, right? And you can calculate the G for any mixture of products, right? But you'll find that where you reach the equilibrium point, which is where you have 2-to-1 ratio, you calculate the Gibbs energy of that point, that arrangement of the molecules at that temperature and pressure, and G is equal to 0. Now, if you think about it, I just said that G is less than 0 for a product-favored reaction. Right? So we'll have to think about what that means. What that means is that the delta G is 0 and that the Gibbs free energy is decreasing as you go from products to reactants, but the instantaneous free energy goes to 0 at the point of equilibrium. Right? So there's a slight difference between what I say G and delta G. Right? And it's kind of, you have to be very careful of Gibbs energy. I'll spend a good amount of time on this probably in next week. Right? But just try not to get caught into that thing where you could have the Gibbs energy at a certain point along a reaction may be 0, even though the delta G for that reaction report may be positive or negative. Okay, so we'll have to distinguish between those two types of G's, if you will. They're the same thing, but they're just defined slightly differently. Right? So what we find is that in a reaction, even if it's product or reactant favored, there's a point along the curve of G. It's a function of the concentrations of the reactants and products where G is 0. And that's where equilibrium is reached. Okay? So we'll have to think about what that means when we look at it more carefully. But in the meantime, it's just like enthalpy. It can be positive, negative, it can be 0. Any questions so far? Okay. So what this means is that what's happening is, so let's go back to our water example now. All right, so let's just kind of roughly look at what this means for water. And so we have H2O, liquid, goes to H2O gas. All right, and we saw that delta H, standard evap, is about 44 kilojoules per mole. And at 373 at boiling, it's about 40. All right, what I want to do now is I want to calculate, what I now want to calculate is delta G vap. Right, what is the Gibbs free energy of vaporization at standard conditions? Well, that's going to be delta H of vap minus the temperature, which is 298 in this case, times the standard enthalpy of vaporization. Right, some enthalpy, or some entropy rather. What the hell is this? Right, we haven't introduced this yet, right? Remember how we defined HVAP? Remember that HVAP, as you can see, I've been changing notation, is equal to the enthalpy of formation at standard conditions of the gas minus the enthalpy, standard enthalpy of formation of the liquid. Right? So what is the entropy of vaporization? Well, it's the same thing. It's going to be some sort of standard entropy of formation of the gas minus the standard enthalpies or the entropies of the liquid. Right? Same concept. But again, the first question we asked about the enthalpies, this is the first question we're going to ask about the entropies. Where the hell did we get these from? Right? Remember how we got to these enthalpies of formation, right? We built them up from little atoms, right? Our little standard atoms, and our standard molecules, right? And we measure differences with respect to them. So maybe we should do the same thing for entropy. But again, entropy is kind of a tricky thing. And let me tell you why, because I'm going to introduce finally the last postulate of thermodynamics today. The one that I've never mentioned to you, and it's now finally time to think about this. It's because now the question is we kind of understand how we get zero enthalpy, right? Using these formations, right? It's a relative energy scale that uses chemistry as our baseline for thermodynamics. So what is our baseline for entropy? What do we define as the 0 point for entropy? Well, unlike enthalpy, entropy has a well-defined 0 point. Right? There is entropy has an absolute scale. Right? And that's the third law called the Nernst theorem, the Nernst law of thermodynamics, the final postulate in our set of postulates that we introduced about 1.5 million years ago. We've been kind of using these postulates, that entropy is a maximum, that the energy is at a minimum at equilibrium. We've learned these postulates, but there's just one more historically. All right, so again, the goal here, what is the scale we use to measure standard entropies? Right? And that introduces the Nernst postulate. Well, if you look it up in the book, this is called the third law of thermo. I don't like using the laws because they're not really laws. They're just postulates, things that we assume to be true. Right? And the Nernst postulate is really simple. For a perfect crystal, perfect crystalline material, the standard entropy of that material goes to 0 as T goes to 0. Otherwise, S approaches some constant value as T goes to 0. Okay. This defines our absolute scale. All right? So what this means is that if we can take a material that's, let's say our reference are our crystals of our individual atoms. Crystal diamond, right? Diamond is a crystal of carbon. The idea is that we take a piece of diamond and cool it down to 0 Kelvin, absolute 0, then its entropy will disappear. Okay, remember what entropy is, right? Entropy is the energy required to fill all the possible arrangements and motions of the molecule in your space, right? And so if at T equals 0, there are no motions. So the entropy goes to 0. There's only one arrangement of the system at 0 for a perfect crystal. There's only one crystal lattice. Crystal. You'll think about this actually in problem set 3. In some ways, problem 1.1, your result is going to be a crystal, two crystals merged together of your two atoms. Right? And they have the minimum entropy. Right, but not everything's a perfect crystal. Right? As we'll see, there are no perfect crystals, but there is an approach. But the idea is that as temperature goes to 0, that entropy reaches a constant value, a flat line, basically, just for a number. Right? So eventually the temperature dependence disappears from entropy. It becomes a constant. All right, so let me show you some numbers. All right, so some examples of standard entropies. All right, so for instance, our standard carbon, which is graphite, remember that its enthalpy of formation is 0 by definition, and its standard entropy at 298 is 5.7 joules per mole per Kelvin. For diamond, right? Diamond is a crystal, forms a cube, face of a cubic crystal. Is that right? Yeah. I forget. Right? Very simple crystal, really rigid, doesn't move at all. Right? Really, really packed, solid diamond. Right? You guys know what diamond is. It's hard to break. Not deformable at all, right? It's got a really, really rigid structure, does not want to move, not very floppy. Not surprisingly, it has even smaller by factor 2 in standard entropy at room temperature. Okay, and let's just pull up the water ones, right? We're interested in water, gas, and liquid. So how do these compare, right? These are solids, right? So how does it compare now to, let's look at H2O liquid and H2O gas. And why don't we look at H2O solid, ice, as well? Maybe that's worth looking at, okay? Just to get a sense of what the entropies look like. So let me bring my thing over. So again, the best place for entropies is the NIST web book. Let's go look at water. Let's look at the gas phase data. Here's our entropy for gas, 188.835. So this is 188.835 joules per mole per Kelvin. So as you can see, quite a bit more entropy in a gas than a solid. Go figure, right? Solid is packed, the atoms move very little, and crystals are fixed in place. Crystals, they can't move at all. That's the whole point of it being a crystal. They're completely fixed in place, locked in a fixed structure. They have very, very, very little entropy. Right? At 300 Kelvin, how much heat energy does a diamond have? Well, you just multiply this number by 300. That's 600 joules per mole. It's a very, very small amount of energy. Right? Remember that a chemical bond is on the order of 400 kilojoules per mole. Very, very small amount of heat energy in a diamond. Right? But if you take a H2O gas and you heat it up to 300 Kelvin, how much heat energy does it have? Well, a whole lot more, right? 188 times, or about 200 times 300, that's 6 kilojoules. 60 kilojoules, 6 kilojoules. 188 times 300, that's 60 kilojoules, 60 kilojoules. Right, so this has 60 kilojoules roughly of heat energy at room temperature. Right, so let's look at liquid and ice. We'll have to go to the condensed phase for this. The entropy of the liquid is 69.95. And for ice, which I actually don't know where it is on here. We'll find it. I wonder if it's under a different category. Oh, I have it on my. I have it here. Sorry. 3.4 joules per mole per Kelvin. So as you can see, here's the important, really, really interesting thing about phases. So really what distinguishes phases more than anything, I mean, their density, first of all, but the compressibility, right? For instance, a gas is very easy to compress, liquid much harder, and solids you can't compress at all. But the most important, and well, that's related, of course, to their entropies. H2O has no heat energy in it, right? That means that those atoms are not moving around at all in ice water, right? They're very rigid. Doesn't want it to form. There's not a lot of energy being used for random motion in a solid. In a liquid, of course, you have more. Those atoms are now free to move. They fill the space. But in a liquid, you're dominated by attractive interactions that kind of binds things together a little bit. You have higher entropy, but intermediate. And then, of course, in the gas, everything's free to move around and bounce around like nothing is there. And you have a very large entropy. So that the numbers make sense. Entropy kind of correlates to disorder, right? And the more ordered the material, the lower the entropy. One thing that you may notice is that all the crystalline materials, graphite's not really a crystal, it's a solid, but it has a rather rigid shape. It's a pattern of benzene rings all attached to each other effectively. It has a very rigid shape. Ice, they all have very similar values, right? And that's for a good reason, because crystals, as I'll show you this week, we'll talk about water ice. Water locks into a very specific arrangement, and water one, regular water ice, there's only a couple of ways to arrange the crystal. And I mean literally, there's like 2 or 3 or 5 or something. 5 different ways to arrange that crystal structure. And so you're looking at kind of the log of 5 here, kT times the log of, or what's the entropy? Kb log W. W is on the order of a couple, like 5. And as you saw, when your W is small, your entropy is also small. Right, and of course, there's many more spaces for the gas. Okay, so what we can do now is we can take these values, and now let's think about delta G for our water, right, at 298. All right, so let's go ahead and let me just write over here. All right, what is delta G? Well, it's delta H minus T delta S. Okay, so then at room temperature. Okay, and so we can take that. That's 44 kilojoules per mole. That's the enthalpy of vaporization at room temperature, minus 298.15 Kelvin, times the entropy change of vaporization, right? And what is that? Well, that's going to be the gas minus the liquid, so it's about 190 versus minus 70, right? So we'll say it's about 120, roughly. Maybe I'll do that more precisely. So S gas minus S liquid at standard pressure. Temperature is 188.69.95. 118.9 joules per mole per Kelvin. Okay, so that's our number. And again, not surprisingly, the entropy is increasing, right? Because we're going from an ordered liquid state to a disordered gas state, so it's positive. So let's go ahead and put that in here. So that's plus 118.9 joules per mole. All right, notice I have a disagreement. Right, this is always one of the students' like general screw-ups when they do Gibbs, is they forget to convert the kilojoules, or 1 to joules and 1 to kilojoules, because entrophies are reported in joules and enthalpies are reported in kilojoules. You always have to multiply one by 1,000 or divide the other by 1,000. Just make sure you pay attention to that. And let me pull up my fancy calculator. So basically this is 44,000 minus 298.15 times 118.9, and this is equal to plus 8.5 roughly kilojoules per mole. Okay, so what this says is that the system, right, it needs 44 kilojoules per mole at room temperature to boil the water. But the entropy of the system, right, the flask, the air in the flask, everything, the total entropy of the process in the system, the experiment, isn't sufficient enough to compensate for the requirement of that energy. Right? You need 44, but the system doesn't have enough to give you. In fact, there's a discrepancy of 8.5 kilojoules per mole. You're short by roughly 9 kilojoules. So what does that mean? Well, that means it doesn't boil, right? There isn't enough energy to get the system to completely boil. So this means, again, not spontaneous. Does not boil. Okay, when we look at equilibrium later on, what we'll find, and in fact we may even start looking at this as soon as next week, what we'll find is that even though it's not spontaneous, even at room temperature, a little bit of that liquid water goes into the gas stage. There's always an equilibrium. Right? So this number tells you roughly what that distribution of gas to liquid is, and it's majority liquid, but there's still a little bit of gas that equilibrates out. And it turns out that roughly at an atmospheric pressure, it's about 40 torr. It's about, what is that, like a 3/100ths of an atmosphere. It's a small amount of gas. Small amount of gas gets involved. Yeah, it's about 5%. 5% in an atmosphere, 1/20th of an atmosphere of water vapor exists at room temperature. Okay? So the whole thing doesn't spontaneously boil, but you do get a little vaporization. right? Because there's enough entropy, if you will, in the system to vaporize some of the molecules, but not all of them, right? Not a majority. All right, so let's look at this at 373 now. Now here's the problem. I can't just take this equation necessarily and just plug 40 in here and then plug 373 into T. Because here's the thing, entropy, like enthalpy, also changes with temperature. Let me show you that. So the enthalpy change, the standard enthalpy of the liquid or the gas, is also varying with the temperature of the sample in the same way that the enthalpy is varying. And I can show this to you on NIST Webbook. If we go back to the heat capacity data, oops, sorry. Again, the heat capacity, remember, had those coefficients for different temperatures. We can calculate the heat capacity, the enthalpy of formation difference at a different temperature. You can also calculate the entropy at a given temperature. And it's actually not too hard to figure out how this works. So let's come back to this point in just a second. All right, I'm just going to make a note down here. All right, we'll come back and calculate delta G at 373 in a second. All right, but remember that delta H at some T is equal to the standard enthalpy plus the integral from the standard temperature to a final temperature, call this TF, of the heat capacity, dt. Right? Remember, the heat capacity is a temperature-dependent function. Right? But remember, as Monica succinctly noted, that enthalpy is equal to TdS. It's equal to the heat change. Right? So that means that the enthalpy change in a constant volume process is just H over T. Right? And so we could plug this relationship into this formula, and what you find is once you do the math, that the entropy of the system at some temperature is equal to the standard entropy plus the integral of the heat capacity function divided by temperature, dt. Right? You just add a 1 over t factor to it. Okay, so if we know how to calculate the enthalpy, if we know the heat capacity function, we take the integral of the heat capacity to calculate the change in enthalpy. And for the entropy, all we do is we take that heat capacity and divide out 1 unit of temperature and integrate. Right? So it's Cp over T instead. So let's look at the formula really quickly that NIST gives us and see if that makes sense. All right, so the heat capacity is a constant plus a linear, quadratic, cubic, and then 1 over T squared. Remember, enthalpy is the integral of that. So the constant term goes linear, the linear term goes to quadratic term goes to cubic term goes to quartic, the 1 over T squared goes to minus 1 over T, and you get a constant of integration on the outside. S is the integral of Cp over T. So the first integral, the first term will be A over T. That integrates the log of T. B of T divided by T is just B. Integral of a constant is a linear term, Bt. Right? And you can see how these all work out that way. Right? So all entropy is the integral of the heat capacity divided by the temperature. And the enthalpy is the integral of the heat capacity, period. Right? So they're related to each other. So if you know the heat capacity, you get everything all at once. Right? We'll come up eventually with a way to calculate Gibbs energy as a function of temperature instead. So we don't have to calculate each one separately. We can just calculate how delta G moves. We'll do that. So we'll take the differences of this and this times T, H minus Ts, and think about how that adjusts with temperature by itself. That'll give us a really nice formula for Gibbs energy as a function of temperature. So we'll come back to that later. But let's just make an approximation. Right? So let's assume that all that happens is that, let's say the entropy just stays constant. Okay, so the enthalpy is changing from 44 to 40 as we heat up. But let's just say the entropy change is constant, so we don't have to make any corrections to it. So let's just see what happens. Right, so let's look. So we're going to do it at t equals 373.15. And we're going to assume delta S is t independent. Right, and that means that delta G is going to be delta H minus T delta S, which is 40 kilojoules a mole minus 373.15 Kelvin times our entropy change, which is right down here, 118.9 joules per mole per Kelvin. All right, so let's count that. 40, oops, sorry. So we have 40,000, 40 kilojoules, 40,000 joules, minus 373.15 times 118.9. This one is negative 4.3 kilojoules per mole. All right, so what's happened? Well, when we were at room temperature, delta G was positive, right? And we interpret that as, hey, some vapor is coming out, but it's not boiling, right? It's spontaneously staying as a liquid. Not enough energy to boil it. But now what's happened is we've driven the entropy, the temperature up. Now there's more heat energy available for the system to use for chemical work. And now I count, and the enthalpy also drops, right? It's less costly to boil the water, vaporize the water. And I also have more energy available due to the higher temperature. And lo and behold, what happens? Now I have a negative Gibbs energy. And the reason why it's minus 4.3 and not 0 is, remember, boiling point is at 373. And that's where boiling actually is equally likely as not. G should be 0, but here it's negative. And the reason why it's negative is because I didn't correct the entropy. Okay, so if I correct the entropy, this number would come out to 0, as it should. Right? But what this tells us is that now the system now spontaneously boils. Okay, so enthalpy tells you something about the energetic requirements of a process, but it doesn't tell you anything about how much energy you have to do that process. And that's what delta G does. Delta G says, hey, let's take the balance of the requirement of energy that we need for a process and subtract off the energy that we have in our bank account, or that Mother Nature gives us at a given temperature. Okay? And so what delta G does at 373 is change sign from positive to negative, which means you go from not boiling to boiling. It becomes spontaneous at boiling. So boiling. Okay, what time is it? Got 10 minutes. Any questions about that? This is probably a little bit of Gen Chem review, but I think it's important. So what we need to start thinking about again is, how does delta G change with temperature? What does delta G tell us about a reaction or a process other than whether it happens or not? Right? And of course, we'll basically use delta G from here on out. It'll become a very, very important number for us, because it'll be kind of a connection. It tells us kind of the direction in which a process goes. It gives us some directionality. Right? It tells us which direction the process will go in our conditions. So enthalpy tells us the requirements that the process has, but delta G tells us whether or not we have enough energy in the bank to complete that process or not. Okay. What I would like to do eventually is to take this information and go back to phases, right? And then we can start analyzing phase transitions using delta G, right? And delta H and delta S, right? We have these three numbers that tell us a lot about how a process is occurring and what's occurring, right? Delta H tells us about how energy flows. Delta S tells us about how the ordering of the system is changing. And delta G tells us whether we have enough energy in the bank to actually do the process. All right, I want to just look at two very, very simple properties of Gibbs that is immediately very helpful for us. That will come into handy. Just two really, really simple formula that will come into handy when we talk about anything in this class, actually. Once we get to equilibrium, it'll become especially clear why it's helpful. So again, let's think a little bit about how G changes. G is a function of N, T, and P. Right, so I want to write down an expression for dg. Right, so again, we're going to use the same process that we did for energy a month ago. Right, we're going to have a partial derivative of g with respect to t, the constant pressure, times the change in temperature. Let me make sure I have my signs right on this. Just a second. All right, there's a minus sign here. Plus dg dv, or sorry, dg dv at constant temperature, dp, right, plus the sum over all the different components of the mixture, dg d in sub I at constant temperature and pressure times the change in that mole quantity. Right, this is the chemical potential. We've seen this before. This is chemical potential. Which we call mu I. This will become, in about a week or so, we'll actually finally start thinking about this, because this is where chemical equilibrium will start to come in. Right? Imagine now we have a box at equilibrium with A and B, and A can interconvert to B. There's going to be some energy component about how the energy changes as we remove A or add B. Right? That's going to determine our equilibrium. We're going to have this distribution where the energy may go down as we add B until we add so much that the energy starts going back up again. We don't have enough A, so we start making more A, the energy goes back down, and it starts to equilibrate at a natural place where the amount of A and the amount of B minimizes the energy. That's chemical equilibrium, right? So we'll come back to that. We'll think about how the energy changes as A converts to B or B converts to A. That's what this is. Right, so this will be our chemical equilibrium term eventually. We're not worried about that right now. We'll think about it with phases as well, right? Because maybe we want to think about how the energy of our flask changes as we add liquid, remove liquid, add gas, remove gas. Something to think about. All right, so equilibrium will play here. Now, as you might notice, the signs change, right? Remember that in our closed box, so compare this to our original statement a long time ago, which is that du is du over ds minus du over dv. Constant entropy, this is the constant volume, dv plus du dn, right? And remember, we have this negative sign here and this positive sign here. Right? Remember, this is temperature. This derivative is temperature, and this is pressure. Right? So here's that Lagrange multiplier thing that I talked about that I never detailed last class. But the idea is we're swapping u with g, and now instead of entropy as being our intrinsic variable, we use temperature. So that's the derivative of entropy, of energy, is temperature. And now we're taking a derivative of energy with respect to temperature. And here we're taking a derivative of energy with respect to pressure, which is a derivative of the energy itself. So this is kind of like a derivative of energy with respect to a derivative of energy, which is kind of a weird concept. And when you do that, you get these sign changes, right? So the T, the S is positive, the T is negative here. They're the ones that are related. The P is positive because the V is negative here. So there's a sign change, and that just comes from the math. It's just a little technical math thing. And these two things, which I'll label as 1 and 2, have very specific definitions. And they're very, very useful for us in chemistry. Right? If we can find some way to track how the energy or the free energy of the system changes with temperature or pressure, we can learn something about the system by measuring these slopes, right? So we'll see how does the equilibrium constant change or delta G change as a function of temperature or pressure. That tells you something about these two quantities, these two derivatives, and these two derivatives have very logical definitions. So number one, which is dG dt at constant pressure, this is minus entropy. Okay. So again, entropy is how the free energy changes as a function of temperature, right? As you feed in more heat energy or remove heat energy, it changes delta G at constant pressure. And dG dP at constant temperature is the molar volume of the material. Okay. All right, so just like how we said that in our closed box, minus that du dv is equal to p minus p, in the same way that dg dp is equal to v, right? You see how the p's and the v's are flipped here, and the s and the t's are flipped, and it gives you minus signs instead. Right, so we get a minus sign here and a positive sign change on both of them as we flip from v to p. We change our intensive and extensive variables around. As we change functions, we get sign changes. And so what we can do is if we can measure how the equilibrium of the material changes as a function of pressure, that tells us something about the molar volume or the density of the material. And as we change the temperature and watch the equilibrium change, that tells us something about the entropy. Okay? We'll use these a lot in this class going forward. It's going to tell us, these two equations are going to tell us a lot about how to measure phase equilibria, chemical equilibria, properties. Because if we're going to start thinking about how a system goes from liquid to gas, we're going to have to start thinking about how the volume changes, right? From a liquid to a gas, from density to low density. And that's going to have something to do with delta G. Okay? All right, so next class we'll come back to these. We'll start looking at these properties for phases. And this will help us start to classify phase transitions now that we have our tools. All right, guys, have a good one.